let's describe the asymptotical expansion of such integrals when h goes to 0. So for this, so now this part will be really computational. As epsilon goes to 0, integral over Rn e to the I x dx over 2 minus epsilon xx, that's I1 xim dnx. So this limit is equal to the following expression. This integral can be computed explicitly. 2 pi to the n capital over 2, I to the n small over 2, then e to the I pi over 4, the signature of the matrix B, square root of the determinant of B, and then sum over perfect matchings on the set I1 IN, and here we have B inverse M1 M2, B inverse M3 M4, B inverse Mn minus 1 Mn. And this is if n is even. And the integral is 0, the limit is 0 if n is odd. So the perfect matchings, it's the following. Maybe, I want to make sure that I have the most economical setting. Maybe don't use this. It's I sub n, and the perfect matching on this is on the set from 1 to n. So, what is a perfect matching? It's the organization of these numbers into pairs. I1 J1, In over 2 Jn over 2. And these pairs are taken up to permutations of pairs and up to permutations of entries in the pairs. So it's really matching. You match this set into pairs. And it doesn't matter in which order you take these pairs, and it doesn't matter in which order you take the elements in the pairs. So, in this sense, you can think of the perfect matching as follows. Take a permutation which brings the take all permutations which which sort of organize the entities in this way. And then sigma is, just take, so sigma is in Sn, and then in this group you have n over 2 copies of S2 which permute these numbers, and also the subgroup which permute pairs. That's n over 2. So this Cartesian product of subgroups is a subgroup is in Sn, and perfect matchings they can be identified with the quotient space. Permutations modulo the action of this subgroup. So you take any permutation, it gives you pairs of numbers, and then you take the equivalence class of such permutations with respect to action of these flips. So in particular you can see that the number of perfect matchings is the ratio n factorial over 2 to the n over 2, n over 2 factorial. And so you can write this sum if you want. I'll just write it here. So you can write this summation in this way as sum as 1 over 2 to the n over 2, n over 2 factorial, and then sum over sigma in Sn, b inverse I sigma 1, I sigma 2, b inverse I sigma 3, I sigma 4, b inverse I sigma n minus 1, sigma n. So this is if you prefer the summation over elements of the symmetric. So this is the statement, and then let's prove it. Simple. So first, let's look at the integral limit epsilon goes to 0, e to the I over 2 x dx minus epsilon x dx. Well, in this case you can just write it as the conditionally convergent integral x px over 2, which is easy to compute. Say B is symmetric. Let's assume that B1, Bn be eigenvalues of B. Any symmetric matrix is diagonalizable. So we can write this as so then we choose the coordinates. If we choose the eigencoordinates, so that x dx is equal to sum over a from 1 to n capital dA x a squared. So then it will be product over a from 1 to n integral over r e to the I dA x squared over 2 dx. And then depending on the sign of b, so this will be, so integral over r e to the ib over 2x squared dx is equal to square root of 2p, and then e to the I pi over 4, and then the sign of this number b divided over 1 over the square root of the absolute value. That's just an elementary exercise.
Excuse me, but well, this integral diverges. So you
it's conditionally convergent.
Conditionally sense.
In the sense that there is a limit. Well, its principal part is convergent. There is a limit as t goes to infinity minus t goes to. That's it.
So you eliminated, well, you neglected epsilon for this, or
you know,
you just
it doesn't
way to regularize this integral.
I don't know why. Just, you know, if I'll put minus epsilon x a squared here, everybody would be happy. So then there would be no problem. So let's assume that I didn't forget. Otherwise, it's just really the principal value of the integral. But in this case, the limit is equal to the principal value. Okay, so so then it is equal to 2 pi to the power n over 2, and then from each of these factors we will have e to the I pi over 4, the number of positive eigenvalues minus the number of negative eigenvalues, divided over the square root of the product of absolute values. But that's exactly the first factors over there. So this is equal to 2 pi n over 2 e to the I pi over 4, the signature of b, and the number of positive eigenvalues minus the number of negative eigenvalues is the definition of the signature of the matrix, divided over the square root of the absolute value of the determinant of b. Okay, so this is the first part, and the second part, let's compute the limit as epsilon goes to 0, Rn e to the I over 2 x bx plus, let's just see if I will not go to my notes, then
the I to the n over 2 on the right hand side.
n is equal to 0 here. Because it's n small. It's the number of x's there. And I don't have any x's here. Okay. So now I want to add something. Plus yx. Y is imaginary. But just so that we wouldn't get confused with powers of square root of -1, let's just keep it like this. Minus epsilon x squared dx. So if you want to compute this integral, then we just change the variable. X to, well, I'm not mistaken, so we write x as x prime plus I b inverse y. and then this integral is equal to the e to the so it's completing the square. I'm sure you can do it faster. So it will be minus, right? And then it will be plus from there. So it will be I over 2 y v inverse y. And then the limit as epsilon goes to 0, integral over Rn e to the I over 2 x prime dx prime minus epsilon x squared. X prime squared. And so this is 2 pi to the n over 2 e to the I pi over 4, the signature of b. Then this goes in pi y, b inverse y, over the square root of the determinant of absolute value. So, and finally, let's just, what we can do is we can just take the nth partial derivative with respect to y. So let's denote this integral by I of y. So the integral is in question, the one that's that we want to compute. It's clear that it is equal to nth partial derivative of I of y. So at y equals 0. So all we have to do is we have to compute the nth partial derivative of this when y equals 0. So it's equal to these 3 factors and then it's clear that it's a 0 if n is equal to, if n is odd, because there will be an extra y from differentiating this bilinear form, and the integral will vanish. And then if n is even, well, let's see what it will be. So we just have to find the monomial in y1, yi1, yin in this expression. So clearly this will be just the coefficient in the Taylor expansion of the exponent, n over 2 coefficient. So it will be I over 2 to the power n over 2. And then here it will be n over 2 factorial, and then y e minus 1 y to the n over 2 plus higher terms. And these are lower terms. So when you differentiate such expression such when we differentiate this in y and put y equals 0, when you differentiate lower terms, what you will get? The degree lower than n over 2. 0 because you differentiate n times. So the lower terms will be 0. Then from here we will have I over 2 to the n over 2, n over 2 factorial. And then we have to differentiate this thing. So, but this thing is what? It's dn dy by 1, dy by n. And then here we have y k1 b inverse k1 l1 y l1 y k2 b inverse k2 l2 y l2 and so on, and n over 2 times. So you can see where the perfect matchings are coming from, because this is the binomial expression to the power n over 2. So y's appear in this expression naturally in pairs. Okay, so we'll come to this later. Plus, when we differentiate higher order terms, there will be extra y's. And then we will set y to 0, it will be 0 again. So no higher order terms, no lower order terms, only the nth order contributes. And then this is equal to I over 2 n over 2 n over 2 factorial, and then I'll just write this sum over permutations, because this expression, see, the only non-zero terms will appear in this expression when the sequence k1 l1, k2 l2, kn over 2 ln over 2. Only in this case, when it's a permutation of I1 I. Otherwise, it will be 0, because you differentiate so you see you have exactly the same number as differentiations as factors here. Each of these ddy's will kill one of the y's. If you don't have a matching y in this binomial, then it will be 0. So the only terms where this sequence is a permutation of this sequence, only those terms will give non-zero contribution, and in this case the contribution will be simply sigma I1, sigma I2, k1 L1. These are just coefficients there. E minus 1, sigma I3, sigma I4. This is k2 L2, and so on. B minus 1, sigma I n minus 1, sigma I m, k n over 2, L n over 2. Is it clear? Okay, so then this is equal to I to the power n over 2, 1 over n over 2 factorial, 2 to the n over 2, and then sum over sigma from Sn, B inverse sigma I1, sigma I2, the inverse sigma I n minus 1, sigma I n. But that's exactly what we have to do. So that's exactly sum over perfect meshings. So this is so-called Wick's lemma. This is just a very useful fact about Gaussian
Are you sure it's spelled with V and not W?
no, I'm not. I think it's Wick's, like this. Okay. Now, it's very convenient to think about this statement. Well, to just express this the monomials in this formula in terms of diagrams. So how you think of so perfect meshings on the set say 1 to n, you can think of them as follows. You just write these numbers in the sequence, and then you put arcs to those numbers which you match. So something like this. So for example, if n equals 4, there are 3 perfect meshings. So you can match this, you can match this, you can match this. The arcs can overlap. Alright, so then the next statement is another combinatorial, practically combinatorial lemma, which is the statement about formal power series. So, helium. Again, limit as epsilon goes to 0, e to the I over 2 x bx minus epsilon x squared minus I sum over n greater or equal than 3, 1 over n factorial. Here's the sum over I1 In. V I1 In x I1 In. So these expressions, this and this, you can think of this expression as there is also h to the power n over 2 minus 1. It's a formal power series in H. Yes. So you can think of this as a formal power series associated to a function which has the Taylor expansion x bx minus sum over n, well, just 1 over n factorial, sum over I1 In d I1 In. So this is really the nth partial derivative of this function. That's 0, it's the sign minus. And this is the Bij is the matrix of second partial derivatives of f at 0. So this is how you sort of think about these objects. And then the theorem is that this expression, this formal power series, is equal to the standard, and you can use the word semi-classical prefactor, e to the I pi over 4 the signature of B, the absolute value of the determinant, the square root of the absolute value of the determinant, and then 1 plus sum over non-empty graphs with 3, 4, and so on valient vertices. No 1 valient vertices and no 2 valient vertices. H to the power minus the Euler characteristics of the graph. Some weight f that I will explain how to compute that depends on gamma. And then the number of elements in the automorphism group of gamma. So this is the expansion of this formal integral, and these things they are called final diagrams. So that's the theorem. It's nice to give a proof of this theorem. So although it's late, so we still have 10 minutes, and that's exactly how much is needed. Any questions so far? I mean, it's rather elementary computations, just lots of formulae. So, well, the proof is very straightforward. Let's just, for simplicity, let's denote this by Vnx. So let's just expand this integral in powers of h. So then this integral is, and I will skip the limits. Epsilon goes to 0, assuming that it's there. Just the regularization of the integral. So it's the integral over Rn e to the I over 2 x to x. And then we have sum over. So I will expand it in the power series in V3, V4, V5, and so on. So it will be sum over n3, n4, n5, and so on, greater or equal than 0. Then from each expansion, I will have so minus I to the power n3 plus n4 plus n5 plus and so on. Then h to the power 3 over 2 minus 1 and 3 plus 4 over 2 minus 1 and 4 plus 5 over 2 minus 1 and 5 plus and so on. Divided over 3 factorial to the power n3 and 3 factorial, 4 factorial to the power n4 and 4 factorial, and so on. And then v3x to n3, v4x to n4, and so on. And then all this integrated over dx. So let's deal with terms in this sum one by one.
So how did you get to that?
What?
I didn't not at all follow that. What just happened?
I just expanded. You see, I have, say, the first term here will be e to the minus I h to the 3 over 2 minus 1 over 3 factorial times v3. So then I just expand the exponent. So I have minus I to the n3, h to the 3 over 2 minus 1 to the power n3, and then v3 to the power n3. That's the contribution from the first term that's proportional to h. And then in the denominator I have 3 factorial to the power n3 and n3 factorial.
What are these n's? N3 and...
It's this expansion.
Oh, so these subscripts on the ends just keep track of which...
Exactly. From which expansion it came from. Alright, so now let's first look at those integrals. It's I over 2 x dx, and then we have v3 x to the n3, v4 x to the n4, and so on, dx. So we can write this as, there are no so many indices in the world to express this thing. So I'll just write few. So v I1, I2, I3, v j1, j2, j3. There are n3 of those. Then v k1, k2, k3, k4. And so on. There are n4 of those, and so on. And then there is the integral Ix dx Rn, again regularized integral, and then you have the product of corresponding monomials in x. xk1, xk2, xk3, xk4. So there are n4 of these, n3 of these triples. And then we want to use this formula over here. But at this point I want to use graphical notations. So So I'll write the integral x dx of those monomials as the prefactor and then sum over perfect meshings, and then I'll just write it like this. Say some perfect meshing first place, second place, and so on. So these are positions in monomial. So here I would have the index, so it's like I1, I2, I3, J1, J2, J3. So this would be first, second, third, fourth, fifth, sixth, and so on positions. So this is the integral, and then the product of these tensors, of these coefficients, I can write as something like this. The collection of stars of vertices. So here I'll have the indices I1, I2, I3, J1, J2, J3, and so on. And then the resulting expression for this integral, let's say this is I and 3 and 4. So this can be written as all these prefactors and then sum over perfect meshings and here we'll have these graphs N3 of trivalent vertices, N4 of 4-valent vertices, N5 of 5-valent vertices, and so on. And these graphs would be contracted to, these edges will be connected by the perfect matching thing. And so, to be more precise now, I should put here F, and I should put here F as well. Here F as well. And F is just the weight of the graph. So F of disjoint union of graphs is equal to F of gamma 1, F of gamma 2. And the rule is that F of I1, I2, I3 is equal to V I1, I2, I3, and so on. If you have 4 edges coming out of the vertex, then you have 4 of them. And also the rule is that F of an arc at the top, connecting arc, it is equal to B inverse IJ. And so if you, and then what, and then the other rule is that if you connect graphs like this. That's the summation over I1 IM f of gamma 2 with indices I1 IM times f of gamma 1 with indices I1 IM. So then this expression becomes, so we computed this integral. It becomes the prefactors 2 pi to the n, oops, well, and then sum over graphs gamma with n3 trivariant vertices and 4 variant vertices and so on. Then the number of graphs gamma n3, gamma n4 and so on. No. The number of perfect matchings M, which produce the same graph gamma. Because we can have two different matchings here producing the same graph. So if we want to convert the sum of the matchings into the sum of the graphs, we have to take into account these multiplicities. And then the weight of gamma. So this is the, maybe I should stop now. So I'll finish the addition tomorrow. So the idea is that the ratio of the number of perfect matchings which produce the same gamma to all these factorials, this would be exactly 1 over the number of automorphisms of gamma. Alright, so we continue.